in the negative z direction. Okay? So I can write E normal equals to minus QD over 4 pi epsilon naught R squared plus D squared raised to 3 over 2 minus sigma B over 2 epsilon. So therefore, sigma bound, I can write it as epsilon naught chi E times E normal when you evaluate it at the surface. So all I have to do is substitute for this in this expression and solve for sigma B. So sigma B then becomes epsilon naught chi E times by minus QD over 4 pi epsilon naught R squared plus D squared raised to 3 over 2 minus sigma B over 2 epsilon. So all what I have to do is to solve for sigma B. Yes?
Why is the total, the electric field
Normal is,
normal? Why is it negative?
okay, so if you have a point charge here, so that what's a positive point charge, what's the direction of that electric field? It's going to be away, right? So this is the direction of the electric field, right? On the surface. So when you decompose it, you have one component parallel like that, and another component that's pointing down on it. Right?
Yeah.
So the component that's normal to the surface is going to point in the negative z direction. And for a negative charge, the electric field is always towards the charge. So that also points in the negative z direction.
Okay.
All right, so all you have to do is just call sigma B, and this is what you get. So just since I want to complete this chapter today, I'll just give you the results. So I'm going to avoid the algebra. So sigma B, what you get here is going to be a negative of Q Q times by D over chi E over 2 pi times chi E plus 2 times 1 over root of R squared plus D squared. Not root raised to 3 over 2. So that is going to be the bound charge density. Any question? So this is just only based on a physical argument what actually does this point charge to what the point charge does to the linear dielectric medium. Its purpose is just to create these bound surface charges. So once you created these bound surface charges, this is like an empty free space. So you are dealing with these bound surface charges and this point charge. So whatever the potential or the electric field that you want to find in here is going to be just these two charges. So that's what I have done here. The other one is just find the potential in this region, which is given by this. And the electric field is going to be the gradient of that potential. And the polarization is going to be just epsilon naught times chi of this medium times the electric field that you determine from here. And then take the normal component of that and set the equals to 0, then you find it actually the same result. Okay. So you can look at that one in the lecture note. If you have any question, you can ask. Yeah, so this is what I was talking about. So this is the electric potential in the region Z less than 0 that depends on QA. So you differentiate that with respect to Z, set D equal to 0 to find that electric field on the surface, and then find the normal component of the polarization by multiplying with that, and then you will find exactly the same result. All right, so now let's talk about energy in a dielectric system. Energy in a dielectric system. Okay, in our discussion in chapter 2, how did we determine energy of a certain charge distribution? What was the relation that we used? Electrical energy in free space. Electrical energy in free space. You know, in free space, if you remember, we expressed it in 3 different ways, and I even gave you a homework problem that asks you to determine the energy in 3 different ways.
Is the work right?
Yeah, the work is basically with the energy, so that's going to be 1 is 1/2 epsilon naught times the integral of E squared d tau, right? Remember that? And the other one is in terms of the potential, or that's going to be half times the charge density, rho, times the electrical potential integrated over the volume, right? And the other one involves, this is over the volume, and this is over one. Our space, yes, good. Space. So we started from this and derived this one, right? So this one came from energy equals to the potential difference delta V times the charge, right? So we started from that, and we came up with this. From this we derived that. So that is in free space. Now, what we are trying to find here is the energy in a dielectric system. So suppose you have a dielectric media, and inside this dielectric media, you have a certain volume charge distribution. So in a dielectric medium, suppose you have a charge, a free charge, you have a free charge, with charge density, rho. Free. This free charge. So you have this certain volume charge, which is described by the free charge density of free, and you want to add a small free charge into this volume. Okay? So if you want to add a certain amount of charge, so you want to add a charge delta Q free into this volume. So when you add this charge into this this volume charge distribution, which is described by rho free, then what happens? The charge density would change, right? If you add in the same amount of volume, you add extra charge delta Q into the volume, then the charge density changes. All right. So in order to add this free charge into the system, you have to do what, right? So what should be the amount of work that you must do to add this charge into this charge distribution, which is placed in a dielectric medium? So you want to add a charge delta Q, then the work done then the work done. The work that you must do, if I call it delta W, so that is gonna be the integral of the change in charge density, rho free, times the potential, which is a function of position. So this is also a function of position r prime, let me call it, and this one v of r prime, times d tau. So this much work you must do to bring this much charge into this charge distribution, which is placed inside the dielectric medium. So this is the change in full charge density that results from the addition of the small charge delta Q. So delta W equals to the integral of change in rho free times the electric potential times d tau prime. But in a dielectric medium, how do we determine the volume free charge density? The divergence of the displacement vector, right? So we know from Gauss's law in a dielectric media, we know that rho free is equals to the divergence of the displacement vector D in a dielectric media. So if I substitute that here, delta W is going to be delta of the divergence of the displacement vector D times the electrical potential B times d tau. All right? So this is over the volume, wherever you have the charge. Now, this is kind of a small change. So if I try to find the change, here the change is with respect to the charge density, which is related to the displacement vector D. So the change is over the gradient of D. But what if I want to find the change in the potential V and also the gradient of D? What do you do? This. It's like a product rule. So if you apply that, what do you get? This is going to be the change in electric potential dotted with the gradient, with the divergence of, not dotted times, the divergence of D displacement vector, and what? Plus, so now the change